Hola a todos.
Hola.
Hola, hola.
Hola, profe.
Hi.
So I'll wait for one or two more stragglers. Do you guys have any questions while we wait?
I
Open
have a
floor.
question about the homework.
Okay. Carlos.
In the part 3, when we have the proton with the 1 giga electron volt of energy, when we have to calculate the velocity of that electron, but that proton, when we use the kinetic energy, we obtain a velocity superior of that the light velocity. So we have to use the relativistic cinetic energy. Okay. Because the
you should never have a velocity greater than the speed of light.
okay. Because the enunciado, says that we have to neglect the relativistic effects, something like that.
This is for I think it's for scattering the relativistic. Let me check. Let's see. Yeah, so what I was thinking of was more in terms of the cross sections than anything else. But yeah, you will need to calculate it in terms of a relativistic speed. Yeah.
Okay.
But in terms of so I mean, I think I asked for both the 1 MeV and a 1 GeV. Is that right?
Mm-hmm.
Yeah. And so if you calculate the 1 MeV, it's not relativistic.
That means to use to the ionization, the relativistic form of the ionization laws.
Yeah, so what I'm basically what I was thinking was that you did not have to use the full-blown Bethe-Bloch formalism with the third term, which is the term for relativistic effects. That's what I was trying to get at when I was mentioning that. Does that make sense?
Okay. Yes. Thank you.
It just makes the math a little bit easier. Yeah, you certainly you will have to calculate the energy, assuming that there's it's not just a pure velocity, but it's a factor of gamma. Okay. Other questions? Roy, you had started to have one.
Yes. About the last class, when we talk about the power observed, and check the components of the acceleration, perpendicular, parallel, and extreme relativistic case. We can talk about invariant phase space. I am thinking in, I don't know how can I pronounce in French, Liouville theorem. It's a equivalent way in the Hamiltonian mechanics or not.
I'm not following your question.
We can talk about the invariants in phase space.
So there's, I mean, yeah, so there's different quantities can be invariant. And you
Yes.
talk about how you would reconfigure certain quantities so that they were invariant, so that when you translate between them, you drop out all of the gammas and all of the deltas, right? But you're talking about actual phase space. This is what I don't quite understand. Where is this going?
For example, the specific intensity, I think that we can think that it's an invariant, right?
No. So the specific intensity is not an invariant by itself. It's only an invariant when you divide it by 3 times the frequency, frequency cubed. And that's it. Well, that's if it's the specific intensity is per frequency, then it was divided by nu cubed. If it's specific intensity integrated, then divided by nu to the 4th power. And that quantity will be invariant between them. But the issue is that specific intensity I nu, it carries around a factor of I guess it's delta to the 3rd. And nu carries around the factor delta. And so you can always construct ratios of quantities that are invariant. But many of the quantities that we would want to measure are not invariant by themselves. And so it's very tricky to interpret between frames that are moving at speeds, fractions of the speed of light or not. It's tricky to interpret what we actually see, the light we see. And so these are kind of ways of dealing with that. So that we can, for instance, understand what is the true power that was emitted in the rest frame and so forth.
Okay.
Does that make sense?
Okay. Yeah, thank you.
Are there other questions? Okay. So let's begin. Where I'm going to turn your microphone off. All right, where are we? Here somewhere. Yeah. Okay, so last lecture we had started off with some sort of questions of how to pull out the power, and the fact that the power radiated. So the power radiated in the K prime frame, that's the instantaneous rest frame, and the power emitted should be the same. However, we get the power received, which is different from this potentially, but the total power should be invariant because while these two things have gammas, they drop out. And so the total, we then have to think about things in terms of, okay, the total power might be conserved, but the directionality of it is not conserved. And so we went on to calculate what this would be using some of the formalism of the Larmor equation, dividing it into perpendicular and parallel components, transforming those, and we get very severe transformations of both of them. And so we then could calculate what this solid angle was, and we did some transformations, and we ended up having the power coming out as a solid angle actually had a very strong transformation. And then we also considered whether it was the power coming out that was emitted or the power coming out that was received. And there's a difference by one factor of this here difference. And so, right, we can go ahead and calculate it and give you a couple of different cases. And so in a couple of sort of extreme cases when the acceleration is purely parallel to the velocity of the moving frames, then this all simplifies down to something like this. This simplifies, and we end up with this expression for how the power is coming out from the parallel component of the acceleration. And likewise, we can do the same thing for acceleration in the perpendicular direction only. And again, not quite as elegant, but we can calculate it. And so we have something which is a little bit uglier to calculate, but nonetheless gives you an answer of how much power is coming out. And so these are the two sort of extreme distributions. And the reality is probably something in between where we have a mix of these things and we have to decouple it into the different components. And so when we then move to very extreme relativistic cases, you had a dipole which looked like this or like this in the instantaneous rest frame, and it would be transformed and look something like this in the observed frame. And so most of the radiation comes within an angle that is sort of order 1 over gamma, 2 divided by gamma. Okay, so that's where we stopped, right? And hopefully it was sort of clear how we ended up getting these extreme beaming effects. And so if you were to integrate over the entire thing, right, then you would find that you would have to some extent the conservation laws, right? In terms of the emitted power, it would be fully conserved. In terms of the received power, it would be different by this factor of 1 minus beta cosine beta. Right, so it still gets a Doppler boost from going from the emitted to the received frames. Right. Okay, so that's probably the simplest case, and so there's we can imagine more complex scenarios, and one which I think is interesting to envision is thinking about an observer sitting on material that's moving out. So you have the outgoing beaming that happens from this change in reference frame, but there's the other effect, which is this particle in the rest frame is seeing the universe in a different way, right? So the light that's coming in from our frame into the frame of the electron, which is initially doing the beaming, the external radiation field that it sees will be different from the one that we see. And that's kind of interesting. And so we can give a very useful case is, imagine you're sitting on a jet of an AGN. So you have blobs of material that have been accelerated up to fractions of the speed of light. And this blob is moving out from the black hole and the accretion disk, and there's an entire radiation field which it's moving into. And so the radiation field might be isotropic in sort of our reference frame or in the reference frame of the galaxy, But to the electron or to the blob of material that is moving through it at some speed close to the speed of light, it's going to see that field differently. And this could be light from the accretion disk, could be light from the broadline region, whatever. Basically, what's going to happen is that this moving blob is going to intercept a fraction of this radiation, and it might then interact with it in some way. And so this has some interesting consequences. So we want to sort of examine that. And so the basic question is, okay, what is the energy density seen by an observer which is co-moving with the jet plasma particles? Right. So we have some energy density of radiation, which is sort of isotropic and maybe uniform outside of that frame. And we want to translate it into what the blob or the jet plasma particles see. And so, I had initially given you this case, right, which is that we have some particle which is moving with respect to us and is emitting isotropically. And what happens is that in our frame, all this radiation is beamed in the forward direction of the velocity. And you also get that this radiation, which maybe was initially red, gets Doppler shifted to be blue. Right, so you have those two effects going on. So we want to imagine the other case, which I just mentioned, which is, okay, we have our black hole, we have our blob moving out, and in this frame, we see, well, let's go to this frame first. So we have this blob moving out at this speed, and this is the radiation that it sees. So radiation is coming in from all sides, it's isotropic. And so when we Lorentz transform back, what happens is this isotropic radiation now becomes, or appears to the blob to be coming from a very small cone of angle 1 over gamma. And of course, this has interesting effects, right? Because now, rather than sort of averaging over some symmetry, you now have all of the radiation coming in one direction, and all the radiation appears blue. And so it's higher energy. And so other processes can come into play, right? So this will give you a different version of Compton scattering. This will, because you have this strong forward symmetry here, you can have a different interaction depending on the cross-section, right? If the cross-section is forward or back symmetric, but maybe is strongly dominated by something in the forward direction or the rear direction, this scenario will give you a lot more, higher cross-section for scattering than this would. And so you get some interesting interplays between those. So just to forward this along a little bit, so let's say we have a co-moving frame, K prime, and the observer will see the photons now coming in from a cone with a semi-aperture of 1 over gamma. And we can think the other half might be hidden by the accretion disk or whatever. So that's where this scenario comes in. So we just have this half, and the accretion disk is hiding this half here. Although the accretion disk will also be emitting, and so it'll have its own thing. But that's another lecture down the line. So let's then imagine what happens. So the photons coming in from the forward direction will be seen as being blue shifted by a factor of this, right, a factor of delta. And if we recall that the intensity shifts as the total intensity will shift as this, basically, intensity times delta to the 4 equals intensity of the K prime frame. That's going to, then if we try and integrate this radiation density over some solid angle, what are we going to get? So you can imagine that this energy density is proportional to I integrated over solid angle, which is going to be 2 pi in this case, when it says it's a hemisphere, and divided by C. We want to integrate I over this solid angle here. And we only need to integrate here from 1 to b in this sort of scenario where we are taking this derivative of cosine in this way. We've kind of already forced the substitution. So this thing, we can plug in what I is. And so we have, plug in this thing, which is this, and it has a cosine term in here we need to integrate over. And this is not a pretty integral, but one can do it, or you'll lookup table and we get something out like this. And so here we have our energy density now in terms of the K frame, but with this correction factor, right? And so depending on beta, you will get a fairly strong boost. So if the frames are traveling, close to the speed of light, you will have something which is not uniform but is boosted. And so, right, if beta is about equal to 1, then we have that the apparent energy density ends up being boosted by a factor of almost 7/3. If we had a full sphere, then this would only be boosted by this gamma factor, a gamma squared factor. But because we are just using the hemisphere, which has most of the photons, we're focusing them in, we end up with this extra boost here. So that's just accumulating all this radiation into a sort of smaller cone. That's what this effect ends up doing. We also have the fact that if we're thinking about the monochromatic energy density or the monochromatic intensity, we will have a Doppler shift as well. And so if we have a monochromatic flux in K, in K prime, what we want to end up looking at is a frequency difference between this and this. And this will give us our small increment of frequency. And it turns out that this flux will end up having a slope, a frequency dependence that goes as nu prime squared, which is not necessarily intuitive, but comes from the fact that you have this transformation here, and this is equal to this transformation. And so if you want to integrate over some small solid angle, then you want to do this integral here. And so in doing this particular integral, it turns out that mu has frequency dependence, or you can set it up to have a frequency dependence. And so this d mu here ends up having a frequency dependence which goes like that. So when you end up doing this integral, you have to integrate over this, and you end up with the fact that you end up having v prime squared here, and then the initial frequency in the K frame was v naught, and so you substitute in v naught for the third here to the third power. And so this is where this dependence comes in. And so it's sort of an interesting Doppler boost, if you will. So what ends up happening here then is if we end up integrating over these frequency limits over this hemisphere, then we would still, if we integrate over all of the frequencies, then we would still return something which looked like this. So we'd still have this dependence, which went as this. But we have in terms of the frequency dependence, it looks something like that. Okay, so that's just one example of the complexities that one has to sort of deal with depending on the geometry of the situation. Later on, we will talk about the opposite effect, which is you have something which is either moving away or moving downward, and how does this accretion disk look to it? And so you then get interesting interplays between electrons, which are moving rapidly here, and the light that's coming from the accretion disk. And so you can get, the light's going to be focused, right, from this disk in this direction here towards this electron that's moving downward now. And you then can have an enhanced Compton scattering or Compton upscattering, right? So the inverse Compton effect. And so there are interesting physical situations where these relativistic transformations are very important. Okay, is everything clear here? You have any doubts?
I have a question related to this plot, to this picture. So the idea is, well, the meaning of this is that, for example, in the case of the AGN, for example, an observer placed on the jet, for example, would see that the radiation field, for example, from the torus or the VLR region, would see the photons more energetic that actually were emitted?
Well, so an electron going this way, for instance, would see this radiation field, everything in front of it, as coming from a smaller angle and being Doppler shifted to bluer energies. So the radiation field in the ionization cone, for instance, the jet would see that as enhanced and more energetic. The radiation from the disk itself, right, if it's moving this way, is actually going to be diminished. And so it's not going to be strongly affected, even though it's a huge source of energy. There's a huge amount of light coming from the disk. But because it's moving in this direction, this is going to be down boosted, right? It's not going to be relativistic beam, it's going to be D-beam in a sense. If the electron is going in the opposite way, and this is more for the X-ray corona, where you have energetic electrons, which are going in all directions, right? Not just being beamed out, but some are going down, some are going up. The electrons that are going down are going to see the disk in a very different way than the electrons which are going up or to the side. And so you have to account for, the fraction that are going down are going to be able to inverse Compton scatter this radiation from the disk much better than the ones going up. And so, if you have a corona and you have a certain distance above the disk for, you have to, okay, some fraction will be upscattering, some fraction won't be. So you have to account for that. It's your bookkeeping thing.
Okay, thank you.
Any other questions? I'm just giving the AGN because A, it's my field, and B, it's an easy example to visualize. But there are other examples like GRB jets, which are moving through the internal structure of a star, which also will have some interesting effects. Or even at very high redshifts, you will have the CMB, which will act as a radiation field, and so you can have an interplay there. Potentially. Okay. So the other sort of interesting thing to come back to is this, we talked a bit about it at the start of maybe the last lecture, or maybe the start of this lecture, the start of the chapter. So when we actually started to measure radio jets with VLBI back in, I guess, the mid-80s or so, you notice that the jets were clumpy, they weren't continuous structure, and they had several radio blobs or knots. And people would go back and observe this again and again and saw that some of the blobs were not stationary, but they were moving out. And of course, this is a projected distance because they don't know exactly what the orientation of the jet is. And so when they looked at these maps and they compared the angular offsets between one epoch and the other, right? So you just have a time. So say we observe it in May of 1985 and then in June of 1985. So it's 30 days. And they would measure some angular offset. And in projected distance, this blob would appear to be moving faster than the speed of light. And they went, wow, this is crazy. And they dubbed this motion superluminal motion. And so, knowing the distance, one can take this angular change and make a linear size change. And so you can then sort of look at the arrival time difference between the two radio maps, and you can estimate an apparent velocity. And so this angle times d gives you r, and this change in the arrival time between the different epochs gives you delta a, and this, it turns out, this can be greater than c. And so how can this actually be? And so just to sort of explain it, we have the, as we had talked about when we were originally looking at this sort of diagram, this arrival time can be much shorter than the delta emission time, right? Because the arrival time is just this here. It's the different, and whereas the emission time is this total thing. And so we can have an observed displacement here, which is this CB, ends up being this quantity in this geometry. And if we then divide CB, which is this physical distance, by our delta arrival time, which we had calculated to be this ends up being this apparent velocity, right? And so we have that, and we can divide out some of these things, or substitute in delta TA and delta TE here. And so what we end up getting is an apparent velocity divided by c, which is related to this angle. And so there are interesting consequences here. So as this gets bigger, right, then this thing gets larger and this thing gets smaller. And so, or I should, sorry, not smaller. Yeah, well, actually it gets smaller. But if you have some intermediate sort of extreme, so I guess, yeah, if this is 90, this is 1, this is beta, this is 0, and so we just have beta. And so this is moving, at its proper speed. If we have 0, then this is 0, and this doesn't matter, and so the apparent velocity is 0, right? Because it's coming along our line of sight. If this is, say, 45, can we do the math here? It should both be square root 2, right? So then this thing ends up being 1 minus square root 2 times, sorry, square root 2 times beta. And this thing ends up being higher than 1 in this case. And so that is this apparent superluminal motion. And so just to sort of ask yourself, for one, in this sort of equation, gamma doesn't appear. And is that okay? Is that reasonable? And for the most part, it should be. It's mostly just that the gammas, they divide out. But you can still plot things in terms of gamma. And so we can look at how this apparent value changes as a function of viewing angle for a different gamma. And of course, beta and gamma are related. So it's, even though gamma isn't here, you still have beta in here. So the velocity is still there. It's just this ratio of sine versus cosine that's important. As I mentioned, at 0, the apparent velocity is 0, and that should be okay because it's just coming towards us, right? So there is no superluminal motion. And at 90, it's moving away from us, and we don't get any boosting. And the big trick question is sort of at what angle is this maximized for? And this will depend on the speed. Because the maximum here is the multiplication of beta times sine theta and beta times cosine theta. And so this is a nice little figure just to show you as a function of gamma where this maximum would be, right? So for gamma equals 10, this maximum occurs at about, sort of 5 or 6 degrees off of our line of sight. For a lower gamma of 2.5, then the maximum occurs at something like 25 degrees. And so forth. Okay. Is there a way to decouple the apparent superluminal speed and the angle? Or can you measure this, based on the superluminal motion? Can you figure out what the real motion of the emitting material is? Do you have enough parameters? Or I guess what else, so you measured this. And so there obviously is a degeneracy between these two things, right? And so if you know one, you can break down the other. But if you don't know both of them, then you can't say for sure exactly what it is. And that, of course, is a problem. There are ways of getting at gamma via other arguments. And so you can use those other arguments to put limits on gamma. And then that obviously puts a limit on beta here. And then you can estimate or get a limit on theta. And so you can estimate roughly what the angle should be. And we'll come back to those later on, when we're talking about the actual emission mechanisms that generate the different types of radiation. Okay, any questions about this?
Yes, one fast question.
Sure.
The maximum in the distribution in beta, the first graph, it follows some law, right?
Well, I mean, the maximum is very close to the gamma, right? So in essence, if you have gamma of 10, the maximum is going to be beta equals 10. If you have gamma equals 20, the maximum is going to be beta equals 20. But that's only that's only at the certain angle. But yeah.
I have another question. In the diagram of the previous slide.
This one? Or this one?
No, this one. The apparent velocity.
The apparent velocity. See.
Yes. So we see that this photon, I think.
Well, this thing is in the previous example, which was I think lecture 3A maybe. We were talking about this as a lamp, which turned on, right, and turned off. And so what we're doing here, originally we were measuring it as what is the extra component when we factor in that this information travels by light, but this lamp is moving. We had to deal with the Doppler shift of this thing, or the arrival time difference, or because the light is traveling and this thing is traveling, and we have to take the difference of those two along our line of sight. the superluminal motion is the same scenario, but just measuring the apparent motion when we can resolve the system, what the apparent motion on the sky is, and how it appears depending on this angle. It can be apparently moving faster than the speed of light. And all that comes down to is the same fact that we have a difference between the emission time and the arrival time, right? Or how long the lamp is on.
Okay. So the apparent velocity we see between the point C and B.
Correct.
Okay.
Yeah. How fast is B moving away from C or from A, right? So, I mean, ultimately it looks like A is the center and B is a blob moving out. And so what we want to measure is this distance here, which is the distance on the sky. And just putting it in a geometrical sense where you actually see that this distance hits right here. So this thing, the light that's emitting, goes here, but when we'd taken a snapshot earlier, it was here. And so we have to subtract off this component to really understand, or we have not necessarily subtract off, but we have to take into account that component to really understand what's happening. Does that make sense?
Yes.
Okay.
Yes. Thank you.
Anything else? All sorts of fun things that occur around relativistic or different reference frames and motion, one transforming to the other. That's non-trivial.
I have a
Okay.
question.
Mm-hmm.
So I understand the situation, but I don't fully understand why this apparent velocity is greater than C in some objects.
Right. So I mean, it comes down to the fact that this thing has been moving a fraction. It has some velocity in this direction, a fraction of which is going in our direction, and so you have light which is emitted, and you have this thing moving at some fraction of the speed of light, and so this distance is going to be less than, not necessarily the distance, but the when this thing turns off, for instance, the distance traveled here will be something, but the difference here won't be this full distance. And that difference means that when you divide this distance by the speed of light to get the time, you are assuming it had a shorter amount of time that it traveled, and therefore that it was faster than the speed of light.
Okay, sorry, but why won't they be the same distance?
No, so so this comes back to lecture 2A, I think, lecture 2A. Yeah, this was here's this one here. And so we had here that this thing emits some light, and the light starts traveling to D. And it takes a certain amount of time to travel to D. During that same amount of time, the lamp moves this distance. And then it turns off. And so the total time that this is the when it started, and the light took a certain amount it traveled a certain distance. And this is when it turned off. And so we will see a time interval here. And that time interval will not be equal to this. It will be shorter. Because while this thing was on, it was moving towards us. at a fraction of the speed of light. So it was catching up with the light,
Right.
right? And so the actual arrival time will only be this distance here, difference,
Yes.
right? And so that the TA is in general, in this particular situation, is less than TE,
Okay. Okay.
right? And so if you were to convert that into a speed, which is what you would do if you measured this distance here, you would end up seeing that it's moving out much faster than it
Okay. Okay. Yeah.
than it should be, right? Physically. That's all. And it's a weird geometrical effect that has to do with this transformation and the fact that light has a fixed speed.
Okay, thank you. It was the same problem, really. I don't know why I thought it was something different happening.
Yeah, no, I just took, I stole this figure. It's not quite the same as the lamp being on, but it's an object moving in this direction, and you end up getting the same effect from it.
Yes.
Okay, any other doubts? Okay, so in the next 15 minutes or so, I want to start talking about Bremsstrahlung through free radiation. So let's put that away. Let's come back here. Okay, so we talked generically about an electron being accelerated and generating some light, and using the Larmor equation, relativistically transforming it, and so forth. And so now we could ask, that's great. How do we actually accelerate an electron? And this is the first of many ways we can accelerate an electron. And so we can imagine that we have a let's say we have a hydrogen region that's just with neutral hydrogen, and we photoionize it, or we collisionally ionize it. And so we break apart all the electrons and protons. And so the electrons have their charge and the protons have their charge, opposites, of course. So we have this plasma, right? And in this plasma, you will have interactions between charged particles. And those interactions will impart forces on those said charged particles. If you put a force on that charged particle, you accelerate it, and thus you can generate radiation. And so it's a sort of natural place for this to happen. So what we're going to do here is, ideally we want to do this with a quantum dynamical treatment, but we're going to start with a classical approach as we did before. And this will give us some idea of the dependencies, and then we can add the quantum mechanical corrections to this. We're also going to look at this first in a non-relativistic case, and then expand to a relativistic case. So, if we have collisions between charged particles in a hot ionized plasma, we can imagine that we there's, I guess, 3 different types of collisions we can have. So we can have electron-electron collision, we can have electron-proton collision, we can have proton-proton collision, right? So generally, we can have radiation associated with the collisions of each of those particles. However, the electron-electron collision and the proton-proton collision, those are equal mass interactions. And so in our dipole approximation, the center of mass of that dipole ends up being equidistant between them. And in general, we end up having a 0 dipole approximation for them, because the dipole moment is proportional to the center of mass. And so the other factor, of course, is that the the maximum velocity that we can achieve. Well, actually, sorry, that's to do equal mass particles. Then the other thing you have to imagine is that, okay, we have an interaction between an electron and a proton. Both of them could potentially emit radiation. And so one thing to sort of consider here is that the maximum velocity acquired by the electron is going to be roughly 2v when the electron mass is much smaller than the proton mass. What that also means is for the proton, it's going to gain or lose a very tiny amount of its energy. And so, you know, the electron will gain a huge amount of energy or lose a huge amount of energy, whereas the proton won't. And so most of the work and most of the radiation that comes out from this sort of scenario ends up being done by the electron. And we don't see almost anything from the proton. Okay, so you know, we could do the calculations for all of this in great detail, but you know, these arguments will play out and kind of limit us to where we should focus our efforts. And so the idea here is that we'll consider two different particles, an electron and an ion. So it doesn't necessarily have to be a proton, but it could be a heavier ion as well. And so in this collision, the electron here is going to be the primary radiator, and we'll assume that the ion is left unaccelerated, right? Because these accelerations are inversely proportional to the mass, whereas the charges are equal. Okay, so when we're going to do this calculation, we're going to break it down in a couple of different steps to simplify things. And so the first one is we will look at a single collision, and we will look for, you know, a given electron velocity and a given impact parameter. And what we want to do is calculate the power spectrum that comes out. What is the amount of energy per frequency that comes out? Then we'll play the game where we integrate over the impact parameters to get the emission for a single electron. Then we would integrate over a thermal distribution of electron velocities to get what the overall spectrum will be from some ensemble of electrons. And then ultimately we will consider not only emission processes, but absorption processes, which will come into play. And so we'll probably talk about these two or three things, and we'll leave this till next week. Okay, and so this free radiation, or Bremsstrahlung, which translates to breaking radiation, what this ends up being in this sense is that this interaction between the protons or the ions and the electrons ends up slowing down the electron, and you radiate away some of the energy from that interaction. So let's start with our electron. It has a charge, not a change. It should be charged. And it's going to be moving in the vicinity of an ion with a charge, which is the atomic number, or the proton number times E, right? The electron has a speed v. It has an impact parameter b. And so we're going to use a approximation here, which is that the electron is traveling in more or less a straight line. And so a deviation from the straight line path is negligible. This is known as the small angle approximation. And again, this comes back to when we talked about the ionization losses, any one interaction was not going to change the velocity or the trajectory of the charged particle very much. And it was only through many interactions that you would slow it down or change its vector. So this is again a similar sort of thing. Any single interaction between an electron and a charge shouldn't change too much the path. And this is the small angle scattering regime. when you have scenarios which disobey this, then you have to treat this in a stronger three-dimensional way. So we will start with the fact that we have a dipole moment between the system, and the dipole moment is just related to the charge and this distance, and we can take the derivative of the dipole moment, and this derivative, the double derivative, will be equal to the charge and the acceleration, the derivative of the velocity. And in terms of frequency, we would have the dipole moment would look like this. The double derivative of the dipole would look like this. And this comes back from chapter 3 or so, or lecture 3. No, lecture 3. I can't remember what 3B, 3C, something like that. So we can then take a Fourier transform with this frequency dependence, and we can relate it to a time dependence like this. And we recall that most of this interaction is going to occur over a relatively short time scale, which is related to the impact parameter divided by the velocity. I forgot to substitute a velocity here with a proper V. This is velocity, not frequency. So most of this interaction will happen over this collision time, which is related by this. And so if we have frequencies which are times the collision time, which are much greater than 1, the oscillations in this thing will be, will average over them, and the overall integral will go towards 0. The integral will be very small. For frequencies which multiplied by this collision time, which are much less than 1, then this exponential ends up going to unity. And so we can kind of express this as this dipole as a function of frequency will equal something which looks like this on small sort of frequency timescales, and is 0 outside of that. And this delta V here is the change in velocity during the collision, or this derivative of this velocity. Okay, so with that sort of scenario in mind, we again have this sort of situation, or we can envision the situation we had before, which so this is the situation for Bremsstrahlung, where we have the electron moving past the stationary ion. And remember, for ionization losses, we just have this inverse. And all you really need to do here is just transform this, because this reference frame is identical to this reference frame, right? So we had initially evaluated that the change in our energy, or change in the work done as a function of frequency, was related to some constants and this dipole squared. And so we can plug in what our estimate of the dipole is here, which is just related to, all it is really just saying this thing is delta V, and we move this omega squared over here. That's how we got this. So we can plug in that for this, and the omega squared is squared, so it's omega 4. The E is E squared, and so the omega 4s drop out, the E squareds replace it, and so we have something which looks like this. And this, of course, is akin to this acceleration term that we had before, right? So we can estimate what this is. We recall that the path is basically linear, and that the velocity change is mostly normal to the original path, right? So it's in this direction. These cancel out, and so this is where we will get most of the energy, in this direction. And so we can integrate the acceleration normal to the path, and we end up getting an acceleration and change in the velocity, which looks like this thing. which we had seen before, right? So we had done this this sort of integral with this. This is R here, and this is this Y component. And we've done this integral, and we end up getting something which looks like that. So relatively simple sort of change here, but related to the initial velocity, related to the number of protons in the ion and the mass of the electron in the impact moment. Okay, everyone with me so far?
Here I have a question, a little
Yeah.
question. The term, the term 2p that is divided, the dipole momentum disappear here.
The 2p, where's 2p?
In the previous slide, there is a term 2p divided, the dipole momentum in the case here, in the upper part of the slide, in the lower part of the slide, in the case when omega tau is lesser than 1.
When it's less than 1, you mean?
Yes,
Yeah, so
2p
well,
that is
basically,
divided, but when it's replaced in the next equation, only appears the electron charge square, the omega to the 4 power that is cancelled with the other omega to the 4 power, and the square
the pi,
sorry,
yeah, I was looking for momentum.
okay.
Pi, yeah, so there's 1 pi here, and this is squared. Good question. There should be 3 pi. Is that right? Yeah, there should be 3 pi, if I'm not mistaken. I need to check where that ends up going, because there's I think here there may be some sort of pi hidden in this one as well. Let me think about that. Yeah, I ended up stealing this from something else. So it may be that this may have some odd definition in terms of how it deals with the pi. Let me check that. Because in Rybicki and Lightman, they just go from this to this without really saying much. They say, oh, well, it's some equation back there. And I tried to put it in here, but I may have taken a version of this equation which is screwing up the pi somehow. So let me check.
Okay, thanks.
Yeah, because I mean, yeah, there's several factors of pi, not only one. But there seem to be off here. Okay. Right. So assuming the pi's are carried correctly, we end up trying to calculate what this delta V is. And we end up then having, plugging that in here, or rather plugging this thing in as squared of this, and we end up with this bunch of parameters here. Most of the things of interest are, of course, V squared and D squared. And we've changed our dimensionality here. So instead of omega tau and 1, we now have this as a function of different regimes of the impact parameter as a function of velocity and frequency. And so this thing, whoops, this thing is now a function of the impact parameter. And over where the impact parameters are small compared to this, we actually have this this force, and where they are large compared to this, we end up having 0. So we can then calculate what the entire spectrum will be. So this is for one electron that is passing at one impact parameter around one proton. And so now let's imagine that we have a variety of ions and some density of electrons. So we have an ion density Ni, we have an electron density Ne, and let's imagine that we have a fixed speed of these particles. And so we will have a flux of electrons, and so we have a number of electrons per area per time that is incident on a single ion. And this would then equate to Ne times the velocity. Right, so just the number of electrons coming through times the velocity that they're coming through at. And then we will have a sort of, we want to integrate over all of the different impact parameters that could possibly occur here. And so we would then do this integral of this, change in work with frequency over our cylinder. And we again do this trick of choosing a B minimum and a B maximum. And so then we have here the number of ions and the velocity, that's the rate of them. And then we also have the number of electrons and the velocity, and then the number of ions. And so, and then a factor here, well, the 2 pi is just moved out from this. And so this thing here is the total amount of energy per frequency, per volume, per time for some number density of ions and some number density of electrons with some fixed speed b. And we've done an integral like this before. And so we end up pulling everything out. So we substitute this in, and this ends up being just 1 over b. So dB divided by b. This, of course, is a logarithm. And so we end up with something which looks like that. All of the fun things are outside of that. And one notices that we have, well, a strong function of charge, but that's fine, ends up being a constant. This is a constant. This is the mass of the electron. This is the velocity of the electron, which comes out here. Oops, I forgot to copy this one over there. We have that it's related to the number density of electrons and number density of ions. And it's related to the atomic number squared. And then it is just a slow function of this thing. And so for a medium which is just hydrogen, ionized plasma of just hydrogen, these two things would then be more or less equal. And so the total amount of work that is done ends up being equal to the density squared of this plasma, right? Which is an interesting effect. So if you have some plasma, the amount of radiation that will be coming out is a strong function of the density of both the ions and the electrons. And this will have interesting implications later. Okay, so we can again play the game where we figure, okay, we have some B max, beyond which there's a low frequency asymptotic limit. And so the contribution to the integral becomes negligible. So we don't need to integrate out to infinity, but just to some B max. And that B max it comes back to be roughly this collision time, right? Which is related to the velocity and the frequency, the oscillation frequency. Okay, for the minimum, we could choose 2 things. And again, we can choose this straight line approximation, So this delta V is more or less going to be proportional to V. And this approximation will fail when this ceases to be valid. And so we could impose some B minimum, which was sort of related to these parameters here, which comes back from where exactly? Here. So, right, so we would have, if this thing was approximately V, we move it on the other side and this ends up being V squared. And we move B on this side. All right. So that's one possibility. The other way would be to treat this as a quantum mechanical sort of system and look at the uncertainty principle, in which case you would have a B min, which would be like this. And again, we have this issue of, do we choose the classical approach or the quantum mechanical approach? And it depends on the situation. And so this one will be greater than this one. If this is true, then the classical description works and the scattering process is valid. And so we could adopt this. This is typically the case for electrons which have a rest energy much less than the sort of Rydberg value here. When this doesn't hold, so when the quantum mechanical one is larger, we can't trust the classical approximation. We should use the quantum mechanical. Okay. And so if you compare these, do the ratio, you again get this this relation here, which is akin to this some constants times the fine structure constant and the velocity. And so generally, when the velocity is less than sort of 1% of the speed of light, it's fine to take the classical approach. And if it's higher than that, you should use it in quantum mechanical. So typically what is done is that this is sort of compressed into this factor here, which is called the Gantt factor, which is a correction factor. And so this can be approximated for any situation of velocity and frequency. So depending on what regime you're in. And so this equation then ends up looking like this. And so, I'll show you some plots of this next time. But this was, I think, more or less all I wanted to say, I think. I don't know. I think I have one. No, I guess this is probably a good enough place to stop. I'll come back to so this is, the derivation for the energy, the amount of energy coming out per frequency per volume for time for a given velocity. And so now the trick is to figure out what just velocity distribution we want to integrate over. And so that could be a thermal distribution, which ends up being relatively easy. That could also be a power law distribution or any distribution you could imagine. So we would apply the integration of velocities over this thing. And then of course we'll modify some of these parameters because this is only the energy per given velocity. And so we'll see what happens next time when we start to look at the velocity distributions. Okay, questions? And I'll figure out my pi issue, hopefully.
I have a question.
Mm-hmm.
So I see that the derivation for this formula is very similar to the one for the ionization losses. To replace the particle in the ionization losses with an electron, would we get a similar result to this?
Well, actually, the ionization losses was the same thing. It's just the inverse. And so what we're doing now is just changing the the work done. So that's the amount of the change in energy from this process. And we have yet to, yeah, I guess, so that change will impart impart photons with some spectrum, because we can say, okay, the change versus with time, and we can do a Fourier transform to say, okay, this acts like a spectrum. But they're actually very similar processes. It's only the replacing the two, which is really just a swapping of the reference frames.
Okay. Thank you.
And that's why I introduced it, because I think I felt like it was a useful extra thing to do, which wasn't too hard. It just gives you more insight into some of the different processes. Other things? No? Okay. Well, I will see some of you maybe on Friday during office hours. Otherwise, good. I chatted with Priscilla. She should have the grades very, very soon. She had some questions about exactly how to score things, which led to some delays. So hopefully this will be sorted out. You'll get homework 1 very soon, and then hopefully very rapidly after that, homework number 2, and then homework number 3. The goal is, of course, to have all of the homeworks and pautas and everything available so that you can study for the test, which is not too far away. Yeah. Good. Okay, any other thoughts?
When will be the test, the first test?
The first test is scheduled for the week before the week off. Let me find the web page and I can show you. Hopefully, where's my sharing button? Share. Okay. So, right. So hopefully you can find this page, Roy. It should be linked from Canvas, but this is where I have the entire schedule and all the classes and everything. So May 5th. And probably I will do it during class, but give you some extra time. I guess that will be okay. You guys don't have any, hopefully you don't have any pending engagements after this class, because then you could do it for longer and then it would be fine. But the issue would just be, if we have to do it during class, then it's a relatively short amount of time.
Professor,
Sí, Carlos. ¿Tiene
what
algo?
kind of tools? What kind of tools we can use for the test?
So this is an interesting question. So I think the way I would like to run it is that you could use calculators if you need to. You would do it on Zoom, pushing your computer away. So probably what I would do is have Priscilla or someone proctor it, so they would be there the whole time, kind of monitoring things. And the idea would just be, as long as we can see your workstation, then it should kind of work similar to an in-person test. The only issue would be, we're going to send you the test and you're going to look at it on your screen, and the only thing we can't really monitor what you're doing on your screen. That's the only downside of that. But that will simulate the test environment, I think, which I would prefer to do. Having you just do it where you can look up everything, it ends up being easier. But I think you don't end up retaining as much of it moving forward, which for some of you is important because you will have to take a qualifier, and the qualifier will be more like what I'm proposing for the test. Right? So I would like to get you in the frame of doing that for this test. That being said, the exam will not be just a sample of questions like on homework, but it will have some extra portions which are more, yeah, I would say easier, faster to do. So they're not going to be writing down equations and solving something, but they'll be examining your knowledge. So you might have like a short answer question where it's more like, tell me everything you can say about Bremsstrahlung. Right? And so you would have to go through and say, okay, this is what, how does Bremsstrahlung work? Where is the emission coming from? Where is it going, etc. That would be an example. So you're a little bit harder for the first portion of the class because not that hard, but some of the concepts lend themselves to sort of descriptions more than others. But that's the envision, how I envision it going. That make sense?
Maybe you could guide us where to focus on.
Well, I mean, you will focus on the last 2 months of material.
Okay.
In essence, what you're going to find is that the test will be only 3 sections, and I will only be able to ask a few questions from each lecture, or from each segment of the class, or from each chapter. And so you have to do some self-editing to figure out what's important. But I'm less likely to ask some very obscure thing than some very obvious thing.
Okay.
Right?
Professor, how we should I don't know how to say this, but give you our answers. Like,
So,
should we write them in paper and then take photos?
Yes.
Okay.
Yes. Exactly that.
Okay. Perfect.
And that, so basically, you would have a certain amount of time to do the test, and then you have a certain amount of time to take photos and so on.
Okay. Oh, okay.
Right.
Yeah.
There would be after whatever a lot of time you decide is useful, and
Okay.
I honestly don't care how long you take. Just as you guys have to agree on it.
Okay.
Right. So if you want to take 3 hours, if you want to take 4 hours, I don't care. Priscilla might care because she might have something to do. But yeah. I also need to see if she's available on the 5th to take the test. But that's the idea behind it, is that there will probably be a few sections of, a few of them will be just knowledge. I might have some true false things, so I'll have a statement and you just tell me if it's true or false. I might have a few things where you have to write out, tell me everything you know about this subject, and then I might have 1 or 2 questions which are actually calculate something. So it's not going to be fully based on, it will be related to the homework, but not fully the same as the homeworks, right? It's not going to just be do a homework in 3 hours.
For the calculate part, we can't use some programming tool like Python. I don't know, like a calculator.
So I would say probably you can use calculators. I would be reluctant to ever use too much on the computer because then it becomes easy to look things up. And so the idea is that you have studied sufficiently that you retain the knowledge. And so we're gonna do old school. I'm not gonna ask you to graph anything. I'm not gonna, it will be fairly straightforward, I think. I haven't made the test yet, so we'll see.
Okay.
You still have almost a month for 3 weeks, right? So I'll know better on sort of the end of April what the test will look like. And of course, you should have all week to study. So that should also help. And yeah, it may be useful. I don't know if it could be the case that on May 3rd, I could ask Priscilla to do a review, or yeah, I don't know how useful that would be or not. Not much. Reviewing 12 classes, 14 classes, 1.5 hours is not going to be trivial. But you could have, if you have doubts or whatever, you could also use May 3rd to address any doubts you have. Okay, we're past time. We have several weeks 2 weeks to discuss this anyway, so we can bring this subject up later. Okay. I'll talk to you guys.
Okay, thank you. Bye
Bye
bye.
bye. Thank you.
Bye.
Bye bye.
Thanks.
Bye.